The owner of a new apartment building must install 25 water heaters. From past experience in other apartment buildings, she knows that Quick Hot is a good brand. A Quick Hot heater is guaranteed for 5 years only. But from her past experience, she knows the probability it will last 10 years is 0.25. All right, so probability of it lasting 10 years is going to be known to be 0.25. So that's the probability of success. So I'm just going to make a little note of that. All right, but first, I guess we should define success lasting longer than 10 years. So the probability of success is known to be 0.25 based off of this individual's experience. All right, so the first part of the problem here is to use a normal curve to determine the probability that 8 or more of the 25 water heaters will last at least 10 years. Well, first off, the directions, or at least the title, says normal approximation to the binomial. All right, so I guess the big question here is this a binomial situation? All right, so do we have a fixed number of trials? The answer is yes. All right, so they're telling us that we have 25 water heaters. That's the number of trials. Fixed probability. Yep. 25% chance that it's going to last longer than 10 years, right? Independent events, you can kind of look at it and say, well, if one of the water heaters craps out after 6 years and it was made on the same factory line as 2 of the other water heaters out of the 25, doesn't that increase the chances of those 2 other water heaters crapping out after 6 years? They probably have the same manufacturer's defect. We can't account for every lurking variable. All right, so what we do is we have to make the assumption that this is an independent event. Now, these are all assumptions until we can verify them, at which point they become conditions. So we have verified that there is a fixed number of trials. All right, the fixed number of trials is the 25 water heaters. The fixed probability, that probability of success isn't changing. It's 0.25 because that's a known fact. All right, that was given to us. All right, so 2 outcomes. It's either going to last 10 years or it's not. We know it's binomial, so what does that give us? Well, it's saying to use the normal curve. Well, in order to use the normal curve, I need to know a mean and a standard deviation. So my mean, mu, is equal to NP, and my standard deviation is equal to the square root of NP times 1 minus P, or you could say NPQ. All right. 25 water heaters multiplied by 0.25, number of items multiplied by the probability of success, what is that, 6.25? And then we're taking the 25 multiplying by 0.25 multiplying by 0.75. So far, I don't think this apartment building owner is overly confident that these water heaters are going to last more than 10 years, because the expected value, 6.25, that's nowhere near 25. We don't expect many of these things to last 10 years. All right. So again, it was 25 times 0.25. And then the square root of 25 times 0.25 times 0.75. So we're looking at about 2.165 on the standard deviation. So then we just have to apply our normal distribution techniques to come up with our probability. That's going to be super easy, barely an inconvenience. The reason why is because we have the ability to do that using Desmos. So we're asked to determine the probability that X is going to be greater than or equal to 8. We need a z-score that corresponds with that. All right, so the z-score is going to be z is equal to 8 minus 6.25 over 2.165. All right. Now, in general terms, if you're looking for a general form way of representing a z-score for a binomial case, it's really z equals x minus np over the square root of np times 1 minus p. Because then you can put it all in one shot. And there's ways to clean this up to make it look a little nicer, a little bit more user-friendly. I don't think that that's overly necessary, especially with Desmos. But you might see variations of this formula along the way. You know, some people like to divide out an n to make things a little bit more user-friendly. And in fact, we're going to do that later on. When we're looking for the z-score, you know, all these calculations are wonderful, but we can kind of build around it by saying, you know, like, why don't I just put it all in one shabiggity bangity boom here? So the numerator is fine, but if I want a little bit more exactitude, then I can just, actually it's 25 times 0.25, just put that calculation right in, you know, rather than putting the rounded form. All right, so Z is going to be approximately 0.808. All right, so now when I pop it into my Desmos, I want this computation. I want the probability, do it in blue now, probability that Z is going to be greater than or equal to about 0.808. All right, so on the low bound, I'm looking at 0.808. On the high bound, something big. And that would be my display. And now you hopefully understand why I'm trying to create room, because I'm just going to get this whole Desmos in there. So we're looking at all this information here, but ultimately, all I need is the 0.2095, all right, which rounds to about 0.210 if you're going to 3 significant. In part B, we're going to get the true result using binomial probability, right? Because what we're dealing with are discrete values, right? The big issue that we run into in this case, and this is going to lead to the deeper understanding here, the normal curve accounts for all the decimal values starting with 8 and going on up to infinity, all right? So it starts at 8 and does not get capped off at 25, and accounts for all the rational numbers between 8 and 25, as well as everything beyond 25. All right, so 8.5. All right, 8.9999999. All right, 13.125. You know, all those different decimal values. All right. Now, I can say that if you have 0.125 of a water heater, of a hot water heater, it's probably not going to work very well. All right. So can you technically have 0.125 of a water heater? Sure. I'm sure you could have a couple of hoses, a couple of pipes, a couple of filters, but it's not going to work. It's not going to do the intended job. All right. So how does this result compare with the result we obtain by using the formula for the binomial probability distribution with n is equal to 25 and p is equal to 0.25? All right. So under distributions, function distributions, if you put in binomial distribution in Desmos, so what we would be looking for here, again, is the probability that x is going to be greater than or equal to 8, which means that that's the same as saying the probability that x is 8 plus the probability that x is 9 plus ... all the way up to the probability that x is 25. All right. If we put the number of trials, 25, into our Desmos calculator and the probability of success, which in this case is 0.25, it gives you the option to find the cumulative probability. All right, the cumulative probability. So we're going to do binomial dist 25.25. All right, number of trials, probability of success. Beauty of Desmos is it tells you that information. You check off find cumulative probability, put in the minimum value. In this case, you can create sliders if you want. Minimum value, maximum value. All right, so min 8, max 25. So that gives us 0.273. Okay. So there's a 0.063 discrepancy. So then a question would be, well how do we get to the 0.273? Well, the short answer is, well, we changed number 1 because number 2 is right. Number 2 is using appropriate binomial techniques. We know it's a binomial distribution, all right? We need more area. We need that shaded region to go just a smidge more to the left. When we establish 8 as the x value in number 1, that created a z-score corresponding with the 8. It gave us all the area to the right of that infinitesimally widthed vertical line at z equals 0.808. If we can come up with a z-score, specifically the x value leading to the z-score, that would allow us to capture a little bit more, so specifically capture the 8 as an x value, then we would have what we need, right? But we don't want to go too far. So the general rule of thumb ends up being we can correct for the continuity factor by moving the z-score a smidge to the left, would capture more area. All right. But then the big question would be, okay, well, what's a smidge? Well, what we want to do is come up with something that's it's mathematically sound, but also going to get the job done. So what we could do is let x be equal to 7.5 and find the probability that x is greater than that number. So it gives us a little bit more area to work with because we're moving half a unit away to the left in terms of x, which is going to correspond to a smidging to the left in terms of z, which is going to give us a smidge more area, which might get us where we need to go. All right. And mathematically, if we're talking about discrete values, whole number values, if I say x is greater than 7.5, I'm saying the first whole number value would be 8, and then 9, then 10, and then, everything beyond that. All right. So I would reperform all these calculations, which sounds like it would be a terrible burden and a pain, but really it's taking just this stuff here and replacing the 8 with a 7.5. 7.5 minus 6.25 over the square root of 25 times 0.25 times 0.75. 0.577 would be my cutoff. It smidged it to the left, so mission accomplished there. Let's see what that does in terms of the probability. Not going to be precise because it's normal approximation. That's the one word that I hadn't addressed yet, but it's an important word. We're approximating the result of a binomial distribution using normal techniques because there is always going to be that idea that we're still getting all the values in between the discrete numbers, between 8 and 9, between 9 and 10, between 10 and 11, and so on up to 25. But this got us closer to the true probability, right? The true probability should have been 0.273. We just got 0.281, right? So, it's 0.04 away rather than being 0.06 away, right? It may not seem like a lot, but it's within 5 percentage points, and that's generally considered to be a rule of thumb. And so that would be your solution. So then, it begs the question, all right, well, what do you do if it's a less than situation? What do you do if it's a less than or equal, a greater than? All right, we got the greater than or equal to situation. We already handled that. All right, so the little reminder at the bottom, when using normal distribution to approximate the binomial, we are computing the areas under bars. All right, the bars over discrete variable r extends from r minus 0.5 to r plus 0.5. So that's a little bit of the theory behind it. So when you think about the histogram, if you were creating a histogram and going by count values, there would actually be some space. So around the 1, you're really kind of ducking into the 0.5 and ducking into a 1.5, creating a bar around that. So it does have some width in the interval of 0.5 to 1.5 to give you the 1. All those values would round to a 1. So that's a little bit more of the math. If we adjust the values of the discrete random variable to obtain a corresponding range for a continuous random variable, that's called making a continuity correction. But that minus 0.5 plus 0.5 is going to be kind of the staple of the existence here. So, but in terms of the process, how do we do that? If r is a left point of an interval, subtract 0.5 to obtain the corresponding normal variable. Right? If it's the right point of an interval, add 0.5. Right? So now I'll show you here. Assume mu is equal to 3 and sigma is equal to 1.5. And we're looking to find the probability of getting some value between 6 and 10. And you know what? I'm going to amend this problem to say using continuity correction. First, we convert it over, make our continuity correction. So probability, we're between 6 and 10. This is going to correct to 5.5 to 10.5. So we convert each of these to z-scores based off of the mean and standard deviation. Now here they gave us the mean and standard deviation, so we didn't have to compute it. So 5.5 minus 3 divided by 1.5. So that's 1.67, 1.667. Then 6.5 should be the same thing, the same idea, rational number, 2.333. So then when we pop these values in, you can put it in the fraction form if you want, but the decimal form, if it's rounded appropriately, is fine too. So 1.667 and 2.333. So it's that little sliver of interval. That's what they're asking us for. And we're talking about 0.0379. We're approximating the probability of R, variable representing the appropriate number of successes, being between 310 and 340. If we want to do that, we would use the normal curve with mu equal to, well, mu is equal to NP. Sigma is equal to the square root of NPQ. So we got 500 as my n value. The probability of success is 0.65. So 500 times 0.65 would be 325. Q we know is 1 minus p. So the square root of 500 times 0.65 times 0.35, about 10.665. Number 2, probability that we're between 310 and 340. All right, we need to convert that over to our x values, where x is a continuous random variable from a normal distribution. So I'm going to reduce the low bound by half a unit, so 309.5. And I'm going to increase my upper bound by half a unit, 340.5. That's the width of the histogram, the bars in the histogram component. All right, but then flat out gives it away in the next question. All right. So we need the z-score corresponding to those values. All right. So 309.5 minus 325 over 10.665. Get an approximate value. And then we do the same thing on the high bound. Z is equal to 340.5 minus 325 divided by 10.665. You generally want to try to get the most accurate form of a result, but if you work with 3 significant digits along the way, your answer will have an acceptable amount of variation, so that's fine. We have a fraction x, 309.5 minus 325, and the denominator I could just write as the square root of, just kind of go right back to basics here, 500 times 0.65 times 0.35. And so I get my z-score that way. It's a little bit more accurate. You might get a smidge of inaccuracy, but it'll round to something at least very close at a minimum. All right. So then I do a little copy job and change my 309 to 340. And we see the symmetry there, 1.453. Will the normal distribution make a good approximation to the binomial for this problem, and why? First, we have to establish that it is appropriate that we use a normal distribution to approximate a binomial distribution. Did we have a fixed number of trials? Yeah, there were 500 arctic terns. Right? Was there a fixed probability? Yeah, there was a 0.65 was the probability that an arctic tern would survive the migration from its summer nesting area to its winter feeding ground. Independent events, we have to make that assumption because I am not knowledgeable in this particular field, so I can only go with the information that's given in the problem. All right. Two outcomes, yeah, the two outcomes is either they're going to survive or they're not. Pretty morbid, but that is what it is, right? So then we now have license to use a binomial probability distribution. It's just a question of, right, how is this going to play out? So let's get into the numbers, all right? So first off, I would want to know the probability that z is going to be between these two numbers. So for that, I'll use a normal distribution function. Function, distribution, normal distribution. The mean and standard deviation 0 and 1. Using our z-scores, we're looking at, if I put in my minimum value, negative 1.453 to positive 1.453. Now I'm starting from scratch with this Desmos, so if I want to get a nicer look at it, it'll do a little stretching. Stretch. Yeah, we got it. So it's about 0.854. Now, again, I don't know anything about Arctic terns. I'm just saying that if I'm looking at this scenario, there's 500 Arctic terns. We know about 65% of them typically survive the migration. I want to know, how the probability that within the interval, a little give or take action there between 310 to 340 of them. So that's 62% to 68% of the 500. Is that, what are the chances that that number, that percentage, that quantity is going to return? And it seems to be that we're at a pretty high probability, around 85%. All right, so that's the normal distribution approach. So what we would need to do is use a binomial distribution to see if that plays out the same way. All right. So using a binomial distribution, we have the number of trials is 500. This has all been stated before. The probability of success, 0.65. Probability of failure, complement of that. The number of successes would be between 310 and 340. So we're looking for the probability that x is between 310 and 340. That's straight up binomial distribution. So function, binomial distribution, trials 500, comma, success probability 0.65, cumulative probability going between 310 and 340, about 0.854. All right, so this is the binomial technique. So will the normal distribution make a good approximation to the binomial for this problem? Why? Yes.